Good morning, students. Myself S.J. Bhatmare, taking a lecture on hydraulics 1. In last lectures, we have already completed our 3 chapters. Today we are going to start our 4th chapter, that is laminar flow and turbulent flow. Okay, so in this lecture, we are going to discuss about the introduction of boundary layer theory and related to laminar flow. Okay, so in this chapter we are going to discuss about the laminar flow, their details, and the turbulent flow and their details. Okay, so let's start with the introduction to boundary layer theory. What do you know about boundary layer theory? Okay, so let's start with the introduction. External flows past objects encompass an extremely wide variety of fluid mechanics phenomena. Clearly, the character of the flow field is a function of the shape of the body. For a given shaped object, the characteristics of the flow depend very strongly on various parameters such as size, orientation, speed, and fluid properties. Okay, so according to dimensional analysis arguments, the character of the flow should depend on the various dimensionless parameters involved. Okay, so for typical external flows, the most important of these parameters are the Reynolds number. Okay, that is Re is equal to UL divided by V, where L is characteristic dimension of the body. So in short, boundary layer theory depends on the Reynolds number, that is Re, which is equal to UL upon V. For many high Reynolds number flows, the flow field may be divided into two regions. For many high Reynolds number flows, the flow field may be divided into two regions. First, a viscous boundary layer adjacent to the surface, and second, the essentially invisible flow outside the boundary layer. We know that fluids adhere the solid walls and they take the solid wall velocity. When the wall does not move, also the velocity of fluid on the wall is 0. In region near the wall, the velocity of fluid particles increases from a value of 0 at the wall to the value that corresponds to the external frictionless flow outside the boundary layer. Okay, you can see the image visualization of the flow around the car. It is visible the thin layer along the body caused by viscosity of the fluid. The flow outside the narrow region near the solid boundary can be considered as ideal. Okay, that is inviscid. You can see in the image the flow around the car. Okay. The concept of boundary layer was first introduced by a German engineer, Prandtl, in 1904. Okay, according to Prandtl theory, when a real fluid flows past a stationary solid boundary at large values of the Reynolds number, the flow will be divided into two regions. First, a thin layer adjoining the solid boundary called the boundary layer, where the viscous effects and rotation cannot be neglected. Okay. Then second, an outer region away from the surface of the object where the viscous effects are very small and can be neglected. The flow behavior is similar to the upstream flow. In this case, a potential flow can be assumed. Thus, these are the two regions divided, okay, Reynolds number, the flow. Okay. Then next, since the fluid at a boundaries has zero velocity, there is a steep velocity gradient from the boundary into the flow. This velocity gradient in a real fluid sets up shear forces near the boundary that reduce the flow speed to that of the boundary. That fluid layer which has had its velocity affected by the boundary shear is called the boundary layer. The fluid layer which has had its velocity affected by the boundary shear is called the boundary layer. For smooth upstream boundaries, the boundary layer starts out at a laminar boundary layer in which the fluid particles move in smooth layers. As a laminar boundary layer increases in thickness, it becomes unstable and finally transforms into a turbulent boundary layer in which the fluid particles move in haphazard path. When the boundary layer has become turbulent, there is still a very thin layer next to the boundary layer, and that has laminar motion. It is called the laminar sublayer. Okay, you can see in the image boundary layer thickness, turbulent boundary layer, transition region, laminar boundary layer, velocity v has been shown, turbulent layer has been shown, overlap layer, buffer layer, viscous sublayers has been shown in the image. Figure shows the development of boundary layer for flow over a flat pit and the different flow regions. The vertical scale has been greatly exaggerated and horizontal scale has been shortened. Okay. The turbulent boundary layer can be considered to consist of four regions characterized by the distance from the wall. The very thin layer next to the wall where viscous effects are dominant is the viscous sublayer. The velocity profile in this layer is very nearly linear and the flow is nearly parallel. Then next to the viscous sublayer, it is buffer layer in which turbulent effects are becoming significant. But the flow is still dominated by viscous effects. So above the buffer level layer is the overlap layer in which the turbulent effects are much more significant but still not dominant. Then above that it is turbulent or outer layer in which turbulent effects dominate over viscous effects. These are the four layers: viscous sublayer, buffer layer, overlap layer and turbulent layer. Okay. So after the boundary layer theory, we are going to start laminar flow and turbulent flow. First we will study about the laminar flow. Okay. Introduction. Fluid flow in circular and non-circular pipes is commonly encountered in practice. The hot and cold water that we use in our homes is pumped through pipes. Water in a city is distributed by extensive piping networks. Oil and natural gas are transported hundreds of miles by large pipelines. Blood is carried throughout our bodies by arteries and veins. The cooling water in an engine is transported by hoses to the pipes in the radiator where it is cooled at as it flows. The fluid in such applications is usually forced to flow by a fan or pump through a flow section. We pay particular attention to friction, which is directly related to the pressure drop and head loss during flow through pipes and ducts. Okay, so water in a city is distributed by extensive piping networks. You know about it. Okay, then the pressure drop is then used to determine the pumping power requirements. The pressure drop is then used to determine the pumping power requirement. A typical piping system involves pipes of different diameters connected to each other by various fittings or elbows to route the fluid, valves to control the flow rate, and pumps to pressurize the fluid. The terms pipe, duct, and conduit are usually used interchangeably for flow sections. In general, flow sections of circular cross section are referred to as pipes, especially when the fluid is a liquid, and flow sections for non-circular cross section as ducts, especially when the fluid is a gas. Small diameter pipes are usually referred to as tubes. Okay, understood? The term pipe, duct, and conduit are usually used interchangeably for flow sections. Then, most fluids, especially liquids, are transported in circular pipes. This is because pipes with a circular cross section can withstand large pressure differences between the inside and the outside without undergoing significant distortion. Okay, you can see the images: circular pipe, water 58 atm, and rectangular duct, air 1.2 atmosphere. Okay, then non-circular pipes are usually used in applications such as the heating and cooling systems of buildings where the pressure difference is relatively small. The manufacturing and installation costs are lower and the available space is limited for ductwork. Okay, you can see the image. Average velocity v average is defined as the average speed through a cross section for fully developed laminar pipe flow. V average is half of maximum velocity. You can see the image. V average, that is velocity, average velocity. Okay, according to the figure, the fluid velocity in a pipe changes from 0 at the surface because of the no slip condition to a maximum at the pipe center. In fluid flow, it is convenient to work with an average velocity, that is V average, which remains constant in incompressible flow when the cross sectional area of the pipe is constant. Then the change in average velocity due to change in density and temperature and due to friction is usually small and is thus disregarded in calculations. Okay, the value of average velocity V average at some streamwise cross section is determined from the requirement that the conservation of mass principle be satisfied. That is, m is equal to rho V average into AC is equal to integration AC to the rho U in bracket R dAc, where m is the mass flow rate, rho is the density, AC is the cross sectional area, and UR is the velocity profile. Then the average velocity for compressible flow in a circular pipe of radius r can be expressed as V average, that is velocity average, is equal to integration AC into rho UR dAc divided by rho AC, which is equal to integration to the limit 0 to r into rho UR 2 pi r dr divided by rho pi r square, which is equal to 2 divided by r square to the integration 0 to r in bracket u r r dr. Therefore, when we know the flow rate or the velocity profile, the average velocity can be determined easily. Okay, average velocity can be determined easily when we know the flow rate and velocity profile. Then what do you know about turbulent flow? Okay, you know about laminar flow. So you can see the images. Okay, V average in one image, that is dye injection, and in second image the turbulent flow. So there is a difference between the flows between laminar and turbulent flow. You can see in the image, that is first is the laminar flow and second is the turbulent flow. So fluid flow in a pipe is streamlined at low velocities but turns chaotic as the velocity is increased above a critical value. A laminar flow is characterized by smooth streamlines and highly ordered motion, and in turbulent flow is characterized by velocity fluctuations and highly disordered motion. The transition from laminar to turbulent flow does not occur suddenly. Rather, it occurs over some region in which the flow fluctuates between laminar and turbulent flows before it becomes fully turbulent. Most flows encountered in practice are turbulent. Laminar flow is encountered when highly viscous fluids, such as oil flow in small pipes or narrow passages. Okay? Then Reynolds number. The transition from laminar to turbulent flow depends upon the geometry, surface roughness, flow velocity, surface temperature, and type of fluid, among other things. After exhaustive experiments in the 1880s, Osborne Reynolds discovered that the flow regime depends mainly on the ratio of inertial forces to viscous forces in the fluid. This ratio is called the Reynolds number and is expressed for internal flow in a circular pipe as Reynolds number Re is equal to internal forces divided by viscous forces, which is equal to V average into D divided by V, which is equal to rho V average D divided by mu. Okay, so you can see the image V average and the L length has been shown, that is Re is equal to internal inertial forces divided by viscous forces, that is rho into V square average L square divided by mu into V average L, which is equal to rho V average L divided by mu. So finally Reynolds number is equal to V average L divided by V. Okay, where V average equal to average flow velocity in bracket meter per second, D is equal to characteristic length of the geometry, that is diameter in case in meter, and V is equal to mu upon rho, which is equal to kinematic viscosity of the fluid. Its unit is meter square per second. Note that the Reynolds number is a dimensionless quantity. Dimensionless quantity. At large Reynolds numbers, the inertial forces which are proportional to the fluid density and the square of the fluid velocity are large relative to the viscous forces, and thus the viscous forces cannot prevent the random and rapid fluctuations of the fluid. At small or moderate Reynolds numbers, however, the viscous forces are large enough to suppress these fluctuations and to keep the fluid in line. Okay, so thus the flow is turbulent in the first case and laminar in second case. Okay, so the Reynolds number at which the flow becomes turbulent is called the critical Reynolds number, that is Reynolds CR. Okay, the value of the critical Reynolds number is different for different geometries and flow conditions. For internal flow in a circular pipe, the generally expected value for the critical Reynolds number is RECR is equal to 2300. For flow through non-circular pipes, the Reynolds number is based on the hydraulic diameter, that is DH, defined as DH is equal to 4AC divided by rho. Okay, P, where AC is the cross sectional area of the pipe and P is its weighted perimeter. The hydraulic diameter is defined such that it reduces to ordinary diameter D for circular pipes. So Reynolds number for circular pipes has been equal to DH is equal to 4AC divided by P, which is equal to 4 into bracket pi D square divided by 4 divided by pi D, which is equal to D. So for flow in circular pipes, laminar flow Reynolds number is less than or equal to 2300. For transitional flow, Reynolds number is in between 2300 between 4000, and Reynolds number greater than 4000, it is turbulent flow. You can see the different shapes images. Circular tube DH is equal to 4 into bracket pi D square divided by 4 divided by pi D, which is equal to D. In square duct, DH is equal to 4A square divided by 4A, which is equal to A. Then rectangular duct, DH is equal to 4AB divided by twice in bracket A plus B, which is equal to twice AB divided by A plus B. Okay. So laminar flow Reynolds number is less than 2300. In between 2300 and 4000, it is transitional flow, and Reynolds number when more than greater than 4000, it is turbulent flow. So thank you very much. In this lecture we studied about the boundary layer theory and laminar flow and turbulent flow and Reynolds number. Okay, so thank you very much.